Let's explore the intriguing story of the universe's origins and the theories that attempt to explain it. Traditionally, we begin with the expansion of space. If we reverse this expansion, we reach a point where all space was compressed into a singularity of infinite density, marking the beginning of time. This starting point is known as the Big Bang, a theory that emerged from Einstein's general relativity in the 1910s. However, our understanding has evolved significantly. Can we still assert that the Big Bang was a singular event? Recent research suggests we might avoid the notion of an absolute beginning. The key is determining whether there is a past singularity, where all points in space converge at time t equals 0. Early models by Friedman and Lemaitre suggested all points converge to an initial point, assuming a perfectly homogeneous universe. However, the presence of galaxies indicates irregularities. Could this lack of perfect smoothness prevent the universe from converging to a single point? To explain the universe's uniformity, we introduce cosmic inflation, a rapid expansion shortly after the Big Bang. This theory suggests small smooth areas in the early universe were stretched to form the giant, homogeneous universe we see today. Initially, inflation was described as a brief period of extreme expansion. However, this inflationary period might not stop everywhere. Perhaps it creates bubble universes like ours within a larger inflationary space-time. If this eternal inflation can last forever into the future, could it have lasted forever into the past? If so, perhaps the universe did not have a beginning. The description of the universe has become more complex over the last century. We need to trace our way back in time to see if we find a beginning. We choose a coordinate system for space and time and trace these coordinates back to see if they reach a point where they can no longer be traced. This can happen if some aspect of the system blows up, becomes infinite. We call these points singularities. In standard Big Bang cosmology, there is a singularity in the past where all paths overlap and can no longer be traced. This is interpreted as a time before which there was no space. But there is at least one example where a singularity does not mean the end of space-time: black holes. The simplest black hole is described by the Schwarzschild metric. If we trace these coordinates inward, they blow up in two places. One is expected. At the center, we find a proper curvature singularity. But there is also a singularity at the event horizon, where the time coordinate blows up. It's as if we can't trace time beyond this horizon. We might be tempted to see this as an insurmountable barrier, but we'd be wrong. Just because the coordinates can't cross this barrier doesn't mean space and time end there. You don't bounce off the event horizon. You fall through it. We just need a simple change of coordinates to map through the event horizon free of infinities. For example, Eddington-Finkelstein coordinates allow continuous mapping to the central singularity. The event horizon is a coordinate singularity, similar to how spherical coordinates have a singularity at the poles. We say space-time is extendable beyond the event horizon because a change of coordinates reveals the space beyond. If we switch to a Penrose diagram, we reveal new spaces resembling a mirror universe and a past white hole. These are the fully extended coordinates. But the central singularity remains a physical singularity. No light can be traced through it. It's reasonable to say space-time ends at the center of a black hole. There's no change of coordinates that extends beyond the central singularity. So, what about the universe's beginning? Is there a singularity there? And if so, is it a real end of space-time singularity or a coordinate singularity, like the event horizon? To find out, we need another tool: geodesic incompleteness. A geodesic is the shortest path through space-time in general relativity. It describes the curved path in a gravitational field or the straight path outside one. Light travels on a null geodesic, a path where time doesn't pass for the traveler. Geodesics are usually considered to continue forever into the past and future. But sometimes a geodesic hits a dead end. These are points of geodesic incompleteness, interpreted as the literal end of space-time. The singularity at a black hole center is an example. Geodesic incompleteness is how Roger Penrose proved black holes contain physical singularities. Geodesic incompleteness alone is convincing, but we worry we traced our geodesics in the wrong system, as with the event horizon. Another sign of the end of space-time at the singularity is that curvature blows up. The gravitational field becomes infinite. If we find such a curvature singularity independent of the system, we can guarantee space-time meets a bad end there. Now that we have sharper tools, let's see what we can find about the universe's beginning. For geodesic incompleteness, the answer seems to be that the universe had a beginning. All geodesics, from a thrown ball's arc to Earth's orbit, can be extended back to the same infinitesimal point. This is true even with cosmic inflation. Demonstrating past geodesic incompleteness usually required assumptions, like the weak energy condition, which says you can't have negative mass densities. But things get weird near the past singularity, so it would be nice not to rely on that condition. In 2003, Board, Goose, and Vilenkin made a stronger argument for past geodesic incompleteness without an energy condition. They only needed to assume the average expansion rate was always positive. This led to the Board, Goose, Vilenkin BGV theorem, stating any universe that expanded throughout its history cannot have expanded forever. It must have a past boundary. But can we be sure this boundary is really an end or a beginning for space-time? And what if space-time is extendable, as through the event horizon? Let's look at other criteria for black holes. If curvature becomes infinite, if so, our universe must contain a physical singularity in its past. If not, we need more investigation. This is what Geschnes, Johnny, Ling, and Quinton do in their paper. They applied a curvature test to various universes' beginnings to check singularity's nature. The results depend on the universe's expansion history. The BGV theorem tells us universes that only expanded must have a past boundary, interpreted as a beginning. This study finds universes with different histories don't need to start with a singularity and may not need to start at all. For example, a universe that expanded after contraction or a static phase doesn't need past singularities. But these histories seem to violate certain energy conditions and may not be possible. This isn't entirely new, more a confirmation that you need to break some aspect of relativity to avoid a beginning. Otherwise, they mostly agree with the BGV theorem. Universes that only expanded do have a beginning, but researchers find a case where the BGV theorem can be challenged. An inflationary universe has exponential expansion. A pure exponential function grows rapidly but stabilizes, never reaching zero size in the past. The BGV theorem tells us even this universe must suffer past geodesic incompleteness. There must be a past boundary we identify as the beginning. This boundary can be represented as lower diagonal edges in a Penrose diagram. They represent past boundaries if there's no way to extend a null geodesic beyond them. Except there is a way. This study found a type of space-time that could extend beyond the past boundary. Our universe is described by the Friedmann-Lemaitre-Robertson-Walker metric. It's that smooth, flat, expanding universe. If you add exponential expansion as cosmic inflation or dark energy, the FLRW metric can be a subset of de Sitter space. As researchers showed, it's possible to think of our universe, our FLRW space, as a segment of a larger de Sitter space. The details are complex, but in short, the BGV theorem insists our universe has a past boundary. If there's no way to map a null geodesic through this boundary, we must interpret it as a beginning of time. But the new work shows there may be a place for these null geodesics to travel to, the larger de Sitter space beyond our FLRW universe. If our universe is extendable this way, this might turn the past boundary into a coordinate singularity rather than a real, physical one. This extended space-time may be as illusory as the white hole and mirror universe of the Penrose diagram. But it's intriguing we have a case where it's not obvious the universe recedes into an untraversable singularity. A word of caution, though. For this to work, our universe's section, the FLRW section, needs a smooth transition to de Sitter space. The only way is for the exponential acceleration component, the cosmological constant, to dominate over density fluctuations at our universe's beginning. If these fluctuations are small, space-time is extendable beyond the past boundary, and we may not have a physical past boundary. But significant fluctuations would close the boundary and turn this transition into a hard singularity, eliminating anything before it. Our universe had density fluctuations in early times. Otherwise, we wouldn't have galaxies and planets today. It's interesting that the irregularity Friedman et al. Ignored might make the Big Bang more likely. This isn't good for an infinite past. There probably was a beginning, but the resolution is buried in inflationary cosmology's unknowns. It also awaits our quantum gravity theory because even if the universe approaches infinite density, our physics understanding breaks down before that point. The most impressive thing about this work isn't the answer, whether there was a beginning or not. The current answer is probably yes. The amazing thing is we can hope to answer questions far beyond our reach. Through pure reason, we can learn if there was a beginning to space-time.